So we're really excited to have Durga as our speaker for the MateriAlZ seminar. Dr. Durga Ananthanarayanan currently works at KTH Royal Institute of Technology. And before that, she used to work at GE. And then before that, she got her PhD from Catholic University Leuven, right? If I'm not mistaken,
Yeah.
Durga. And she's done a lot of really good work on integrated computational materials engineering. And in fact, the way I got to know Durga was through Dr. Westman at the University of Arizona, because when he was working at GE, he was involved a lot with Durga, and she had done a lot of really nice work on alloy design and development. So we're really excited to have Dr. Durga Ananthanarayanan as a speaker today. The floor is yours, Durga.
Yep, thanks a lot, Krishna, Ankit, and all the other organizers for inviting me to this seminar series. I mean, it's a real honor for me to be part of this series where there have been so many top experts from different fields. So the topic of my talk today, let me get straight into it. It's about accelerating alloy design for metal additive manufacturing, and primarily from a modeling perspective. As Krishna said, I also worked at GE Research before this, so I'll also include some of my work from there in this presentation. Let me start with a personal story. Some of you may know this is an Indian sweet called Mysore Pak, and it's made of these ingredients. And it also happens to be one of my favorite sweets. And it's something I've made a lot of times with my mother back home in India. And it's a fairly straightforward recipe. You take these 3 ingredients, you follow it, and you end up with these nice cakes. So when I moved to Europe to do my PhD, I've done this before. So I took them, I followed the recipe, and I ended up with something like this, which was crumbly, and it was not really what I was used to. So I did a bit of failure analysis. So I looked at, this is how the heating and cooling profile of when you do it in a traditional gas stove back in India looks like. And if I follow the same recipe in this cooking plate, it actually looks like something like this. So it heats up very slowly and cools down very slowly as well. And that really is not suitable to make the sweet. So I had to do a bit of tinkering and then modified the controls so that I could end up with a similar profile and still end up with this, the right shape and texture and so on. So that's kind of similar to what we have been trying with additive manufacturing, I would say. We have alloys that were designed for casting and rod processing, and we are trying to print them with selective laser melting and other additive manufacturing processes. And no wonder we end up with things like cracks when we do the same. So this is an example from Hastelloy X that was cast and heat treated and rod processed compared to what we see in SLM with a lot of cracks. And now we are trying to find our way to, modify that temperature profile or add some extra ingredients to really get what we desire. So before we get into that alloy design process itself, just a small intro for people who may not be aware of what metal additive manufacturing is. And I'll go right into it with an example. So this is an example of the selective laser melting process. Basically all additive manufacturing processes involve like buildup of the material layer by layer. So here we have in the bottom, first we lay out one layer of metal powder and then selectively melt it in the regions where we want our part to form. And then we'll put one more layer of powder and then melt it in some locations and so on as we build up the part. So this can be done either with a laser, so in which case it's called selective laser melting, or we can do the same with an electron beam instead, then we call it electron beam melting. So this is the powder bed kind of process. We can also, instead of having this powder bed, we can feed the powder simultaneously as we melt it. So that is like a powder blown type of process, which we call laser metal deposition. Then we can have like metallic wire deposition instead of that. And these are solidification based AM processes. There are also other solid state AM processes like friction stir, binder jetting, and so on. In this talk, I'll focus mainly on this solidification-based AM process, and I will mostly only focus on SLM in terms of the examples I give. But the modeling approach itself is not restricted to SLM. I mean, you just have to make sure you have the right conditions fed into the models when you try to apply it to other processes. So how do we go about alloy design in general? So we take up this task of doing the system design chart. So first we look at the process that the material undergoes, and then we relate it to the structure and the properties that we'll get from it. So in the case of a generic AM alloy, if we take, so first we have to make the metal powder. So the powder production is the first step. Then we have the additive manufacturing step itself. And then we can have some further post-treatments like hot isostatic pressing or heat treatment to generate a certain kind of structure or to remove defects and so on. And then through each process step, then several structural aspects are created or modified. So you will have certain phases forming, transforming. Then the grain structure, for example, is fairly fixed by the additive manufacturing processes. But then you can have recrystallization and so on in later treatments. Then you have several kinds of defects that come up, like porosity, cracks, or inclusions, and segregation in the solidification structure. And all of these then influence different mechanical properties like strength, toughness, fatigue, or the cracking resistance, and so on. So to do an alloy design, really, we have to consider all these aspects. So the process structure correlations, structure property correlations to really start with something and obtain the required properties that you want. So in this talk, I'll focus only on a few process structure correlations. So from the additive manufacturing process, how does the phase fraction morphology, how is that formed? Then the grain structure, the crack susceptibility, and segregation. So I'll focus only on these four aspects, but I'll give a bit of more background so that it's easy to extend this kind of approach to other specific structural aspects that you're looking at as well. So a little bit into what happens during the process, really. So this is an example from casting, which we've all seen in textbooks. So you have the mold and you pour in the liquid metal into it. And then the walls, from the walls, the solidification starts, and you have this columnar grains growing. And with time, then the middle portion of the liquid as well cools, and you have sufficient undercooling for homogeneous nucleation, and equiax grains form from here. And this is the kind of structure that we get. But in the case of SLM, then we have the laser beam belting, maybe the first layer and some layers below. And you have a melt pool that forms. And then due to the direction of the thermal gradients and heat transfer, then you have grains growing along that. And the growth rate is so fast that you don't even have time probably for this transition to happen. And we end up with these long columnar grains. And due to these, this type of grain structure and the stresses, that then we have a lot of cracks as well forming. So that's about the grain structure and the cracking. What happens in the case of phases? So this is an example from steel, where at the end of the additive manufacturing process itself, we end up with a Martensite and austenite structure, which is not what we have from, let's say, casting or other processes with lower cooling rates. So the cooling rates already influences the phases that form at the end of the process. And if we look at the inside the grains, they have this typical cell structure. And then across the cells, you have microsegregation that happens. So this is also an aspect that we need to take into account. For example, when we want to post-process this, heat treat it, then the level of this segregation would determine the temperature time cycle that you would have to use for the heat treatment itself. So to study these four aspects then, how do we go about a modeling approach? we need to look at several aspects. So first, the temperature evolution itself, which will determine all of this, then the residual stress, solidification, which will determine which phases are formed, how they segregate, what grain structure forms, and also solid state phase transformation. And ideally, we would need models that solve the temperature, stress, and the phase transformation simultaneously. But here, the focus, as I said, is on alloy design. So we want to be able to use these models for trying out different compositions, the effect of different process conditions. So we will stick to mainly models that are scalable and fairly accurate in terms of capturing the important phenomena that occur. Also, I'll not go into residual stress in this talk. We'll only look at the temperature, solidification, and solid state phase transformation. So first, the temperature evolution. So to predict how the temperature evolves in time and space, we can have several models again that can do this, starting from a Rosenthal type of steady state model, which solves the heat conduction. But we can also use other more and more complex model taking into account transient effects or the coupling with mechanical effects, fluid flow, and so on. Yeah, I also want to point to this nice review paper, especially for students who are maybe wanting to get into modeling of AM. So this is really a comprehensive paper that goes into a fair amount of depth on several modeling approaches for AM. So for temperature evolution, yes, so there is a lot of things we can do. But if we look at, again, from an approach of alloy design, the key things that we need when we want to predict the solidification later is the range of thermal gradients that we expect and the velocities that we expect. And this is typically the range that we find for SLM, 10 to the 5 to 10 to the 8 Kelvin per meter and 10 to the minus 2 to 1 meter per second. Of course, we can, if needed, we can always go back and do more detailed modeling. Next, solidification. So there's a lot of discussion on this. So is local equilibrium valid, or do we need to go to non-equilibrium effects? So first, let's start with the basics. So when we have very, very slow solidification, we always have bulk equilibrium in the system. So if we have at a certain temperature below the liquidus temperature, some amount of solid has formed and there is liquid. And if we want to know the compositions, then we have the Gibbs energies at that temperature, and then we construct the common tangent, which gives the minimum Gibbs energy. And then we can read off the compositions, which is what the phase diagram shows. And then we go to another temperature and so on. But this is not, for this to happen, of course, we need very, very slow solidification, and that's not what happens in reality in any process for that matter. So we have to consider the effect of diffusion. So there is, there are several, levels of approximation we can use here. And one of the most popular ones is, of course, the child solidification, where we assume that there is infinite diffusion in the liquid and absolutely no diffusion in the solid. And this is a fair approximation because typically the diffusion in solid is up to like 3 orders of magnitude or even more slower than in the liquid. But even here, we have this local equilibrium assumption at the interface, which means that every time you have a liquid of certain composition, this new solid that forms at the interface would still follow the phase diagram or the minimum Gibbs energy. So even though there is no diffusion inside the solid at the interface, this still holds. But of course, as the solidification proceeds, we can see that there will be a gradient in composition. So the segregation is still captured by this, but it still sticks to equilibrium at the interface. And one more level of approximation would be to have something like a DITRA type calculation where we allow for diffusion in the solid and the liquid as well, but still maintaining the local equilibrium at the interface. But what happens at very high interface velocity? We go completely away from this equilibrium composition. So we will have something very different from equilibrium composition in the solid and in the liquid. And to understand this, then we look at the Gibbs energy curves again. So suppose we go away from the equilibrium, we have, let's say, a composition Cl, then the driving force for forming a solid of composition Cs is given by this delta G. And then the interface velocity is related to this driving force delta G by this equation, where V0 is the speed of sound. And then, yeah, we see that completely we go to a different regime, composition regime. So from this, we can get probably the composition of solid and liquid. And one more relation that's required to determine this completely is the partitioning of the solute itself. So based on the solute influx at the interface and mass balance, and with a lot of simplifications, we have this Aziz model, which is also commonly used nowadays to represent this non-equilibrium effect. So with these two equations, then we can determine the temperature and the composition of solid and liquid, considering this high interface velocity. And just to show what this non-equilibrium partition coefficient looks like, it is related to the equilibrium partition coefficient, the velocity, and this diffuse interface velocity. I'll talk a bit more about this later. But just to show what happens, so if we have different partition coefficients, ranging from 0 to 1 or above, then at higher and higher velocities, all of them go towards 1. So at very, very high velocities, like we have in glass forming conditions, so then we'll have a partition coefficient as 1. So that was about partitioning and non-equilibrium effects. But the Gibbs energy itself, what we looked at so far, if it's the bulk Gibbs energy, we know that when our system has different morphologies, like say cells, and you have other stresses in the system, then the Gibbs energy also shifts. So we have to add all of these additional energies to the system before we compute an equilibrium or any driving forces. So that also has to be kept in mind. So that was about solidification, all the different phenomena. Then solid state phase transformation. We already have a lot of models accounting for things like diffusion controlled phase transformation, diffusion less phase transformations. And there are several thermodynamic software packages like Thermocalc, Ditra, Prisma, and other models that predict, say, Martensite transformation. All of them in principle can be used to predict AM structures as well from the point below solidification. But one thing to keep in mind would be that we have very different initial conditions that we have to input to these models, because we have a certain level of segregation due to the process, and the phases formed could also be very different because of this extra driving forces that we have, plus the effect of stresses also. So when we capture all of these initial conditions, we can still use the models available for solid state phase transformation. So as we saw in all of these, there are several key input parameters that are required. And one of them is, of course, the Gibbs energies and the diffusion mobilities that we have to take from CalFAT databases. So even though we are not calculating bulk equilibrium, we saw that we still need these as input for our models. So the reliability of these input parameters is of paramount importance. Then we also have thermophysical properties that we would ideally need as a function of composition, temperature, and for different phases. So that's also another challenge that we face in terms of input parameters. Okay, so that was a bit of background on how to approach all these different phenomena. And sticking to these four main topics for this talk, the objective is to see, can we predict these accurately, and can we optimize them by composition and process changes? So that's the overall objective. So let's start with the first part, which is segregation. So as I said, so in this cell structure, we see that composition segregation happens, microsegregation. So we want to be able to predict, what is the level of segregation in this scale. So for this, I give an example from this work that was performed when I was at GE Research, along with intern at that time, Abhishek. So we had a bunch of EPMA data for high gamma prime strength and nickel-based superalloys. And we started with shale, as we do normally, and found that we are not really able to use shale for predicting the solidification path and segregation. So the first approximation that we did was this modified shale approach, wherein we capture the non-equilibrium effects. So it's similar to shale solidification, but just when we calculate the composition of the solid and liquid at each step, we also include the effect of the non-equilibrium partition coefficient. And one more assumption that we do is the fraction of solid of the different phases that are formed. We assume that it's the same as equilibrium, which is not entirely correct, but that's the first approximation that we used. So how did we validate these calculations? So we had this EPMA data. So we had maps of the full EPMA of the structure. So it covered several cells. And then we sorted this data so that we have sufficient points that represent the middle of the dendrite and the interdendritic region. And we sorted them based on known elements like titanium, tungsten, which we know will segregate to the interdendritic region. Then we also had DSC measurements, which when we converted to temperature and fraction of solid. And using this, then we tried to predict using the modified shale approach. So going into this equation for non-equilibrium partition coefficient. So as I said, it's related to the equilibrium one, velocity and diffuse interface velocity. And this diffuse interface velocity itself is related to the diffusion coefficient and also this A0, which is called atomic jump distance, which is related to the interface thickness. So this is something that's not easily, we cannot estimate it experimentally, and therefore it can be treated as a parameter in our models, and we can try to estimate it if we have good data. So that's what we did. Abhishek ran this genetic algorithm and then tried to get closer to the experimental data. And this is what we had. After 25 generations of this calculation, we see that for some elements, so the black curve is the EPMA data and the blue curve is the final generation 25 data, prediction from the model. So we see that for some elements, we are getting closer, but not for all. So, but overall, we at least have similar trends in the direction of segregation, at least for most of the elements. So some more improvement that can be done here. But the first cut is, of course, that we need to include the non-equilibrium effects when we calculate segregation. Next, going to phase fractions and morphology. So for this, I'll take the example of this SLM hot work tool state that we are working with in our group. So here we see that the as-built structure contains martensite, mostly martensite, and some amount of austenite in the intercellular region. So we want to be able to predict these phases forming after solidification and further solid state phase transformation. So when we look at the equilibrium phase fraction of this particular tool steel, we see that at high temperature in the solidification range, first we have the delta PCC, the ferrite, and then the red one is the FCC or austenite also starts to form in the solidification range. And then after some point, the ferrite dissolves. So if we typically start with this information and we want to, let's say, do child solidification to predict the phases and segregation, we see that even there, first delta BCC or ferrite would form, and then you would have FCC forming and then other phases maybe. So if we just used shale, then we will predict that delta BCC, FCC, HCP form at the end of solidification, which is of course not what we see from the experiments. We should see predominantly austenite, which would then transform to martensite. So then this is where the effect of the morphology and interfacial energy that I talked about earlier that comes into play. And of course, we need to also include the non-equilibrium effects. So in order to do that, we use this KGT model for predicting the dendrite growth kinetics, and where we again use this velocity dependent partition coefficient and also liquidus slope. Then we can also calculate the dendrite tip radius, composition, and the interface temperature based on stability analysis. So since we already know that we have this cell structure forming, so we did these calculations then for the delta BCC and the FCC phases. So this kind of model has been used for predicting weld structures and also AM structures, like predicting the primary solidification structure. But I should also point out that these models still use dilute solution approximation for multi-component alloys. So using this model, then what we found was that at lower velocities, we see that delta BCC has a higher dendrite tip temperature. So what this means is when we come down in temperature and hit this temperature, delta BCC can form as a dendrite and it is solidified and it is stabilized. But when we go to higher velocities, then FCC or austenite has the higher tip temperature and then it's stabilized. So it's probably the case that in SLM, where we are in this solidification velocity range, and in the gradients of 10 to the 6 to 10 to the 8 Kelvin per meter. So even in both these values, we see this transition happening at higher velocities. So this is probably what's happening, and that's why we don't see any ferrite in the asphalt structure. So that was solidification. And then the solid state phase transformation also seems to happen because we see martensite and not austenite in our as-built structure. So we also need to predict this solid state phase transformation happening. Sorry. So in order to do this, then we also need to look at the segregation. So this is an example from SLM 18 nickel 300. And this is part of the master thesis of Julia Sjöström, who worked in our group last year. So what she did was look at the temperature evolution using this Simufact additive software. So she had the whole thermal cycling that happens. And we also found from literature that we have the cell structure and segregation in 18 nickel 300 as well. And similar to this tool steel, we also had martensitic transformation happening, and the final structure only had martensite and some retained austenite in the intercellular region. So she did segregation calculations using Dictra this time, and then she found that you have some level of segregation for certain elements like molybdenum, titanium. And we also know that the martensite start temperature depends on the composition. And then from the so this shows the intercellular region, and this is the middle of the cell itself. And in this range, then the martensite temperature would also vary depending on the composition. And she also did this simulation for different cases with varying the base plate temperature. So if you have a base plate that's above the martensite start temperature, then in that region, you would not have martensite transformation happening. And this is similar to what we see in the experiments, because in the interdendritic region, the austenite is still retained in many places. So then we are able to correlate what we observe in the experiments from simulations like this. And as I said, it's not sufficient to just use alloy composition and calculate martensite start temperature. The effect of segregation is important in cases like this for predicting solid state phase transformation. So the summary of these two parts. So we saw that the solidification path depends on driving forces for different phase morphologies, the thermal gradients and interface velocities, and all of these are important for AM. And we also saw that segregation further affects the solid state transformation. And looking forward, I think in situ studies would be very valuable because we have these calculations and we are able to make qualitative comparisons to experiments, but it would be ideal if we could do more quantitative comparison from in situ studies. I think already this work is going on in a lot of places, but relating it to the model would be better. Then we also need to look at further effect of thermal cycling on the solid state phase transformation itself. Sorry, I'll just drink a bit of water. Yeah. So moving to the next part, which is on grain structure. So as I said, we have this typical columnar grain structure that forms in SLM. And one of the activities that's been going on a lot is how to make this more equiaxed, and so that we have more uniform properties, isotropic properties, and how do we, in general, control the grain structure. So there are different ways we can do this. But from a modeling perspective, so what is it that we want to look at is this competition between the columnar growths and the equiax growth. So imagine that this is the bottom of the melt pool, and you have the start of these columnar grains. They grow into the melt pool. And suppose there are effective nucleating sites here for equiax growth, then they would also start growing. And then, yeah, whichever sort of wins, then that structure is predominant inside your melt pool. And using the Hunt and Gauman's model, whether we have the columnar grain or equiax grain finally, it depends on the thermal gradient and the interface velocity, the solidification velocity. So if we have very high gradients in this solidification velocity range, then we probably have fully columnar grains. So we have to go to lower gradients and higher velocities if we want fully equiax grains. So this may not be achievable in many alloying cases. So one way to introduce or induce more equiax growth would be to introduce inoculant particles that have that will act as heterogeneous nucleating sites, and then you'll have grains forming here. So this is also shown by applying the Hunt and Gauman model, that this whole calculation, it depends on a few parameters: the undercooling for columnar growth, undercooling for equiax growth, and the number density of the nucleation sites for equiax growth. So if we have very small nucleation undercooling for equiax growth, that is encouraged. And if we have more of nucleation sites, that also encourages the equiax growth. So in literature, that's been primarily the two ways that we have seen studies that induce equiax growth. So one is playing around with the thermal gradients and velocities through the process parameter adjustments, so that you get thermal conditions favorable for equiax growth, or inducing inoculants like in the study, which then nucleate a lot of equiax grains. So then in our project, we decided to apply this method of using inoculants to ferritic stainless steels. So then if we want to introduce an inoculant, there are several factors that we have to consider. So one, it has to be in the right size range for it to be effective. Then it needs to be of a certain number density, the interfacial energy should be favorable, and the lattice mismatch, and so on. Plus, we also need to have favorable thermal conditions in our process for it to be effective. So when we looked in literature about this ferritic stainless steel, we saw that adding titanium nitride, if it forms, then it can act as inoculant. So here we see with more addition of titanium and nitrogen, we have finer and finer grains. So taking as a base the 441 grade of ferritic stainless steel, we try to design two different compositions, one which does not have any titanium, and another which had the maximum amount of titanium nitride that could form. So we adjusted the amount of titanium nitrogen such a way that we can have maximum amount of titanium nitride forming through the gas atomization process. So we were restricted about the amount of nitrogen that we could add through that. So these two compositions were designed, atomized, and printed. And then we also found that it had picked up some oxygen. So when we look at the equilibrium phase fractions, we see that at high temperatures, we have the oxide-rich phases like spinel in the case of titanium-free material. And in the titanium high case, we have corundum forming at high temperature, and also titanium nitride. So from literature, we also know that this titanium nitride can nucleate on the corundum itself. So hopefully we thought that this would be favorable. So when we printed these two alloys and analyzed them, so we find in the case of titanium high alloy compared to the titanium free, and we also see a lot of equiax regions clearly. So the titanium nitride does seem to work. And this project is in collaboration with Chalmers, so where they are doing a lot of printing and experiments for this study. So what's going on here? A little bit more analysis confirming whether titanium nitride is forming. So when we look at both the titanium free and titanium high material, both seem to have some particles in the as printed structure. And in the case of titanium high, we have bigger particles in the equiax regions, and in the slightly columnar regions that we found, we had like very, very fine particles. And yeah, my colleague Niklas analyzed this further and found that there were very fine oxides in the case of titanium free alloy. And in the case of titanium high alloy, we have titanium nitride encapsulating the corundum particles. That's what the compositions seem to suggest. So how do we relate it to the thermal gradients and the thermal conditions that we have? So typically in a melt pool, we have high thermal gradient and low velocity in the bottom of the melt pool, and low gradient and high velocity in the middle of the melt pool. And from our experiments, we saw that we have very, very small particles in these columnar region, and in the more equiax region, we had bigger particles. So this can be explained by this GRADE model, which looks at the inoculant particle size and the nucleation undercooling required for nucleating an equiax grain on this inoculant particle. So in the case where we have very low velocity here, we can also calculate the columnar growth velocity by the methods I showed before. So here, if we have very low velocity, then the undercooling required for columnar growth is very low. So if we want our equiax grains to form here, we should add big enough particles that have even lower undercooling than this value for it to be effective. So in the case of, in the middle of the melt pool, we have higher velocities. So the columnar undercooling for columnar growth is actually higher. But if we have particles in the right size range, then they have lower undercooling and they take over. So this kind of explains what we see here. So summarizing this part, so the thermal conditions and the nucleating sites, their size, density, and so on determine the extent of CET. And in situ formation of inoculating phase is possible by pre-alloying the powder, as we showed here. And we also saw that the oxygen pickup in the system can be utilized to nucleate inoculating phases. From a modeling perspective, it would be great if we want to do really quantitative predictions of CET, more measurements of inoculant size distribution, and also look at the effect of multi-component interactions in concentrated alloys, and not just use dilute solution approximations. So coming to the final part, which is on crack susceptibility. So yeah, as I said, we have this type of grain structure and a lot of cracks forming if we don't optimize the conditions for AM. So this is actually a result of everything that we saw so far. So the solidification, the grain structure, the residual stresses, the segregation, all of this actually influences the crack susceptibility. Again, this is part of the work that was performed at GE Research. So if we look at the literature, we see that there are several criteria that are proposed, starting from something as simple as a freezing range. Then there is the crack susceptibility coefficient by Klein and Davis, which looks at the time spent in the last part of solidification compared to the last, from 90 to 40%. Yeah, these are more empirical correlations that they see. Something more related to, let's say, the critical strain rate is then proposed by this RDG model or the Cow criterion, which looks at the shrinkage effect and then the overall stresses in the system, and if there is a critical strain rate that is reached, then there is a crack forming. Then we also have this Jang and Singer's criterion, which was specifically for nickel-based superalloys, where they tested a lot and found that this shrinkage, the volume change that happens during solidification, and the strain, associated strain with it, those can be maybe predictors of crack susceptibility. But the point remains that there is no clear consensus, even in the non-AM literature, on what are the reliable criteria we can use for predicting crack susceptibility. So what we did in this project was we had a bunch of high gamma prime content nickel-based superalloys, and all of them were put through the same set of process conditions. So you have this consistent set of data. And then the crack density was measured for all of these different alloys. So we could really compare them, like one of them is more susceptible to cracking than the other. And we used the Scheil solidification path again to evaluate all of these previous, the criteria that I showed in the previous slide. So what we found was that when we compared the mean crack density measured from the experiments to all of these different criteria, there was actually not very good correlation for any of them. So among all of this, I think the cow criterion probably performs the best, but even that is actually not so good at all. So in this case, we tried a different hybrid approach. So apart from this bunch of different criteria, we also took some other related criteria and tried to evaluate which of them has a maximum effect on the mean crack density. And finally, my colleagues, Adarsh Shukla, Sanket Sarkar, and others, so they developed this regression model, which actually captures this much better. So we see an R square of 0.8 when we include these set of criteria and come up with a regression model. So this work will be presented in more detail at Superalloys 2020, which didn't happen in 2020, but will hopefully happen in September 2021. So you can hear more about that there. But the conclusion from this part then is the cracking itself is a very complex phenomenon that depends on so many different factors. And if we want really effective models for alloy design, which are fast and fairly accurate, then approaches such as machine learning may be really useful here. And looking forward, it would be useful if we have more of generic non-alloy specific modeling approaches for predicting crack susceptibility. And of course, the effect of rapid solidification should be studied more in this regard. So we looked at 4 different aspects of the process structure correlation: the phase formation, morphology, the grain structure, crack susceptibility, and segregation. And to do this, we looked at different models. So we saw from the temperature evolution that thermal gradients, cooling rates, these are key input for other models. And from the solidification models, we saw that the interface velocity and the morphology are key if we want to predict things like phase formation. And for solid state phase transformation, we saw the importance of using the right initial conditions if we want to predict them correctly. And as an overall outlook, then we need a lot more accurate and scalable models for alloy design for AM specifically, and a lot of targeted high throughput experiments for model validation for AM conditions are again required. Then this is something I didn't talk about so much, but most of these models are really for steady state. And we know that this is not a steady state process. So these transient effects and how much importance they have if we want to use models for alloy design also need to be explored more. And the multi-component interactions become definitely important in concentrated alloys. So we should not just stick to dilute solute approximations when we use models. Finally, the role of stresses, which we didn't discuss today, but it is quite important in cracking and solid state phase transformation. So that aspect, it's of course very difficult to incorporate. And if we want to do, screening of alloys, because it depends on the geometry and so on. But yeah, some way of incorporating this is essential, and also the effect of thermal cycling. So can we have our cake and eat it too? I mean, can we get away with just process optimization and tinkering with existing alloys to make sure we get the right structure and so on? Or do we need to, or can we move to new unexplored alloying spaces? I mean, from a modeling perspective, at least I can say that we definitely need a lot more model validation to be able to do predictive simulations, but also the thermophysical properties are still not as accurate and as detailed as we would like them to be, and the databases that we have as well. So before I conclude, I want to thank, of course, my funding source for my current projects. This is the DMA project, which is funded by the Swedish agency Vinnova in cooperation with a lot of companies and Chalmers and different competence centrum as well. Then the Hero M2I, again, it's a competence center in which we are working on this materials design project, again, with cooperation with different companies. And we really cover a lot of different modeling tools which companies can take forward and use for their own material development. And most importantly of all, I want to acknowledge and thank all of my current and past collaborators, colleagues, mentors. Yeah, this is our work, really. So thank you very much. Looking forward to your comments and questions.
Thanks a lot, Durga. That was like super informative.
Thank you.
Any questions? I think Ankit, people will be posting it on the chat, right? I think there was Ankita who had 2 questions.
Okay.
Ankita, do you want to post your question?
I want to ask the questions.
Yeah, go ahead. Sorry.
Okay. Hi, ma'am. I just the question is a bit long. I just wanted to understand when you are putting an inoculant in the matrix and you're expecting an oxide growth. I just wanted to understand, how do you incorporate the free energies? Are you also incorporating the free energies of the inoculant, or and I mean, is it affecting your phase field simulation, the specific inoculant which you're using? And when the oxide is growing in the matrix, so are you how are you putting this in the phase field conditions, like with the Gibbs free energies? How are you incorporating this in the model?
You mean this particular calculation?
Yes,
Okay.
exactly.
So this is just done from thermocalc using the TCF11 database, Steele's database, and it already has this Gibbs energy functions for all of these different phases. So I mean, this is a straightforward calculation. So this is just equilibrium calculation for using the different Gibbs energies.
But the oxide was not there initially, correct? It had evolved.
We're not simulating in real time what happens. So this is just equilibrium calculation. So this does not take into account first forming the oxide. And I mean, that's what we would ideally want to do. But for this part of what I showed, it's more explaining what we see. Yeah, not really predictions.
Okay.
Step by step, this is what forms.
Okay. And next question is, when I was what I was asking, if you are doing non-equilibrium phase field modeling for Martensite, then how exactly are you in the phase field model? We know that we require the equilibrium condition. So, and along with the segregation, how are you modeling that?
Okay, firstly, I didn't show any phase field modeling at all in this talk. So it was only looking at things like driving forces.
Yes.
Yeah. So for the Martensite, so this one. Okay. So here there is a Martensite temperature and fraction prediction tool within the latest versions of thermocalc, which is based on driving forces purely again. So it just looks for that composition if there is sufficient driving force for the Martensite to form and predicts that.
Oh, okay, okay.
But
So
your
you got.
question was, sorry, I missed your full question.
Yeah, I was saying, like, how would you use it, the Gibbs free energies at every point of the evolution? How would you use it for non-equilibrium solidification?
Okay. It would be indirectly, for example, if you take this model, it would come in indirectly when you try to calculate the equilibrium partition coefficient and equilibrium liquidus slope. So to calculate that, I mean, you need the Gibbs energies function. That's how it's calculated.
Okay, okay. And do we, and also segregation is once you set up the simulation, do we also get the segregation, or we have to include any specific conditions for that?
For which simulation?
For the segregation which you were showing.
This one or the earlier one?
In the red graph, I think you were showing some. Yeah.
This one, yeah. So here, yeah, we will get both the, yeah, so this is a procedure that we follow, and we will get both, yeah, the phases that form and also their compositions. Yes. So that we will get the segregation. Yeah.
Okay. Thanks a lot.
Yeah, thank you.
Anyone else?
I think, Krishna, we have another question from Ariel.
Oh, yeah. Ariel, do you want to go ahead and ask your question?
Hi, yeah, so can you hear me?
Yeah.
Okay, sorry. I was wondering if there's any effect on the solidification cracking or the grain structure if you're using recycled powder.
Recycled powder. So, I mean, I personally have not studied so much on that. So even this data set that is showed here, so I mean, it was made sure that all of these were really virgin powders so that we didn't have any effect of all of this when we try to do the modeling. Because I mean, we already have so many effects that we don't use in the model. So that would be one more thing added unnecessarily if we start using recycled powder, I think so. But no, I mean, I'm not, yeah, so I don't have so much information on this, unfortunately.
Okay.
Yeah. Yes.
Durga, I have a question, may not be the smartest one, but so far you haven't taken into account any of the process parameters per se, right? Is there
so yeah, so the process parameters would come in indirectly through the temperature evolution. So that's something now we are trying to do more quantitative studies of, like, can we look for different process parameters at the melt pool scale? Can we do some modeling and then correlate it with the segregation, for example? So
yeah.
Yeah,
I know that you did touch upon the heated build plate and its role, but that may probably have some more quantitative effects.
I think, yeah, Julia did a lot of work on looking at different process parameters. I think her thesis is available openly, so you can have a look at it. But there she really looked at different process parameters, different base plate temperatures, and since she was using Simifact additives, she could really simulate the full temperature profile as well. Yeah.
Cool.
Can I ask a question?
So one point maybe, sorry, I'll just mention this point, but we also saw that, at least in this case, that once we go below the liquidus temperature and stay below the liquidus temperature, solidus temperature. Yeah. So if below the solidus temperature, so even these further small peaks, they didn't seem to have so much influence on the segregation.
Yeah.
So the first solidification or the last solidification kind of fixes the segregation. Yeah.
Okay. I know that someone else had a question.
Yeah, I think Christina
I was just like started talking. Sorry.
Yeah.
I have sort of a goofball question. I really like the talk. Thank you. And these are beautiful microstructures. and morphologies.
Thank you.
In your experience, is there an element that stands out as like behaving the weirdest? Like in a way that you would at least expect, or like completely different from others when you like hit them with a laser? Is there such an element, or are they still all kind of the same?
Okay, you mean across alloys? So if we do this to
Yeah,
one,
if you do alloys,
or-
if you do alloys studies, and I
Yeah.
apologize, this is a goofy question, not very
no,
scientific.
I think
You
it's
seem to
interesting.
have
But
a lot of
firstly, I should.
experience, so
Yeah, no, but firstly, for all the nice microstructures, I should thank my colleagues Niklas and Jaying. So it's all theirs that I'm showing. So I'm only the modeling person. So first confession. But I think, yeah, of course, I didn't start. I'm not doing AM for 10 years. So from the moment I started working on AM around 2016, 17, I think everything has been, okay, oh, really? Is this how it's happening? So, I mean, I was not working on welding before, so that's been the case. But really, I think what we see in these steels, it's really fascinating. I mean, not something that we would expect. So even in this case, we were probably expecting a full martensite, not retained austenite. And then, okay, we have to go back and look at the segregation. It still segregates so much. So it's not, still above the MS temperature in some cases and so on. So I think those have been really fascinating to look at. The inoculants now, I mean, it's still kind of a mystery because we want a full equiax structure. I mean, we still have a lot of columnar grains here, so we are not so happy with that. So again, not something that we expected, maybe.
Yeah, that looks like art. That's just beautiful. Yeah, thank you.
Thank you.
Yeah, I have a question. So yeah, thanks for the really nice talk. And I'm not doing additive manufacturing yet, so maybe I'm late to join. So, yeah, I mean, a lot of the modeling studies, and I know from your background on free field models, and also stuff people do with Dictra and thermocalc. So a lot of these methods actually rely or basically assume growth process, or they sort of try to mimic the growth process or model it in one way or the other, right? However, I don't think there has been enough attention given to the nucleation kinetics of this part. And I think morphology of a microstructure is going to be governed by as much as a nucleation as much as by the growth. So what's your comment on, maybe you can maybe elucidate the status of modeling nucleation in some of these processes?
Yeah, I think, that's one of the challenges that I think we see in other studies as well, that they comment at the end of the day, okay, we can do phase field modeling, we can do CA, we can do so many things, but we don't know what the nucleation kinetics looks like. So unfortunately, that remains a challenge. So one of the things, at least, that we are trying now is to have more, as I mentioned here, more quantitative measurements of this inoculant size distribution, because even here, since we do in situ formation of inoculants, so it's actually pre-alloyed and we're not adding it as particles externally. We still need to predict this in the models really if we want to do quantitative modeling. So there first, of course, having the data is important, and we are doing trying to do a lot of measurements there. There have been attempts at doing this. And as you know, one of the key parameters, if you want to model the nucleation, is the interfacial energy. So, I mean, I think the way ahead is probably a lot of atomistic calculations and trying to go bottom up rather than just assuming or trying to fit these parameters based on the experimental data. Yeah, that's my opinion. Yeah. But it's a real challenge, I mean, for all the models that I mentioned here.
Thank you.
I think Mahesh had a question. Mahesh, are you online or you left for lunch? So I'll read out the question, Durga. He first compliments you by saying it's a very informative presentation. Then the question is, have you studied whether the elements segregated in the interdendritic regions can be completely homogenized by post-thermal heat treatments? And what's the effect of HIP?
Okay. Yeah, I'm not an expert on HIP, so I can only give a general answer about HIP maybe. So yeah, typically it's used to relieve the stresses a little bit and close small pores, small cracks that are closable with that. And of course, along the way, since you do it at a high temperature, you would have some homogenization effect as well. As far as the segregation goes, yes, for this case, with this tool steel, my colleagues again, Niklas Jain and Rita, so they are working on looking at the effect of heat treatment on these materials, and it is possible to actually homogenize because it's really micro segregation, and the distances are small, so you can really diffuse and you can homogenize these materials, at least in this case. Yeah. But the advantage would really be, can we avoid a lot of post treatments and still get something that's usable? I mean, that's where this whole, trying to control the grain structure also comes in. So we want to avoid too much of post processing. Really. Yeah.
So in general, Durga, what are your, I mean, where do you see this? I mean, where do you see the state of the art at this point? I mean, are we just still solving ICME for AM case by case, or are we at a stage where, the CalFA or thermocalc or Dictra is black box enough, or I can integrate it with SimuFact or ANSYS, and even a non-expert, I wouldn't say, I mean, still a material scientist, still someone doing manufacturing can start using it. If no other questions, I think let's thank Dr. Durga Ananthanarayanan once again for this fantastic talk.